Today we have with us Tom Suchanek. Did I say that right? Correctly? How do you say it?
Close enough.
Okay.
How do you say it?
Suchanek.
Suchanek. Thank you, Tom. Scientist emeritus from the U.S. Geological Survey Western Ecological Research Center at UC Davis. We also have Diz Swift. And she's going to, both of them will tell you a bit about their credentials in this area of climate change so that you'll have a better understanding of how they came to the information they'll be sharing with you today. So, are there any questions before we begin our program? Tom, I believe you wanted to go first. Oh, I'm sorry.
When Tom gets up, I was asked if you could all shift down. We're videoing, and unfortunately the lady on the end is in the screen. So if we could just, when Tom gets up, if we could just shift down, I would really appreciate it.
Cool. All right, so without further ado, Tom Suchanek.
Thank you.
And no.
Oh, I thought Tom was going first.
Please explain it. Tom is speaking about the science, and then I will speak about the policy.
Well, I'm going to let Tom do that.
Okay, then Tom, please explain
Thank you, Karen. Appreciate it. I think this room is small enough. There's 4 things I have to hold here at the same time. So I'm just going to put the water down and the microphone down. Can everybody hear me?
Yeah.
Okay, good. That's 2 more things I don't have to hold. I have to hold this one, and I might have to hold this one. Anyway, great crowd. Thank you all for coming. I'm glad that we can at least share some things about climate change. My credentials, background, I was at UC Davis. Well, first of all, I got a PhD at the University of Washington in marine ecology, and then moved on to the Virgin Islands for 3 years doing research on coral reefs, and then out in the South Pacific for a while, and then, I moved to UC Davis and was a faculty member there for 20 years, teaching courses on marine invertebrate zoology, ecology, oceanography, a host of other types of classes, and also during that time, I was the Western Regional Director of the National Institute for Global Environmental Change. That is a Department of Energy program to fund scientists to do research on climate change issues, carbon flux in the western United States. So I did that for 7 years. And then I moved on to the U.S. Fish and Wildlife Service, where I was heading up their Environmental Contaminants Division for several years, and then went on to the U.S. Geological Survey, where I was lead scientist and climate change coordinator. Just retired this last year. I'm already wearing out my chaise lounge. And, doing things like this, trying to interact with the public and inform them what kinds of things are happening around us. I probably don't need to inform you what things are happening around here. And other places, you're seeing it on the news, on the radio, on the television, on the internet. Everywhere, things are changing. So what I'd like to do today is basically talk about the science of climate change, both here in California and basically around the globe, because everything is connected, everything is happening here that's happening elsewhere as well, with a subtitle, To See or Not to See. That is the challenge. So I want to show of hands. How many people think they know what to see or not to see means? And I'll give you a clue, it's not Shakespeare's Hamlet. Good, okay, about a third of the audience. We're going to visit that again in a little while. But right now I'd like to go on and start, you don't want to trip over that, talking a little bit about the science. So we know that our world is changing around us, and if we could hit the lights over there, Joey? Perfect. Is that okay for everybody? That's good for me. Things like temperature are changing, rainfall, snowpack, seasonality, fire. Well, speaking of which, we had a great sunrise in Sacramento this morning. You probably all have been listening to the Butte fire. I think it's over 100,000 acres now. It's just terrible. Sea level rise, ocean productivity. All these things are changing in our world. And the question is, what are we going to do about it? How can we address this issue? And where is this all coming from? So if there's nothing else that you take away from this talk today, there's a couple things that I really would like you to have. One is that variability in the climate is a key, variability in a lot of things, but also to expect, actually not expect, we're experiencing already unpredictable and extreme weather events, as you all very well know. However, we still have time. We do have time to make a difference in our world, in our landscape, to give our children and our children's children a better place to live, or at least an acceptable place to live. And that's the key right here. We're trying to provide information that will help future generations. I think we need to start out with the basics, just so that I'm sure that most people understand all of this part already, but I want to start out with a good background here. The greenhouse effect, which is really what we're talking about here, is a natural phenomenon. The sun beats down on the earth, sun's rays and radiation pass through the atmosphere, hit the earth, warm the earth. Some of that heat is dissipated back through the atmosphere and ends up back into space. Some of it is trapped because of greenhouse gases: carbon dioxide, CO2, methane, CH4, and nitrous oxide. Those are some of the main greenhouse gases, but there are many others as well. Human-enhanced greenhouse effect is very similar. We have the sun doing the same thing, heating up the earth, reflecting heat back through the atmosphere. Only because there's more of these greenhouse gases, more of that heat is trapped in the Earth's atmosphere. That's what's happening right now. The Earth is heating up. There's no question about that. And we've known about this for a long time. By early 1800s, we knew about heat-trapping gases and the effect on temperature of the atmosphere. This fellow right here, Svante Arrhenius, was the first person to actually write a climate model. By hand, in the 1800s, took him 2 years. By hand. And his wife left him. So I don't know what that says about us scientists and how we're going to survive this by putting all of our energies and efforts into doing science. But we have a lot of information now because there's thousands and thousands and thousands of scientists working on this problem right now, all around the world, in dozens and dozens of countries, and they're working hard at it. 97% of the climate papers that are published that deal with the position on human-caused global warming agree that, number one, it's happening, and number two, that it's human-based, it's human-caused. I like to think that scientists are the map makers. We're providing the information, and you guys, the citizens and the policymakers, are really the navigators. We're going to give you the information. You can do with it what you think is best, pass laws, refute laws, and navigate us to a better place. So I think that's a good place to start this. For the next 45 minutes or so, or maybe 15 minutes or so at this point, I hope to transmit some information about the science. What data and what information do we use to study climate change? We have modern things that we can measure: global temperature and tidal gauges over the last 150 years, atmospheric carbon dioxide being measured since 1958, altered phenologies, that's first bud and flowering times, bird nesting, migration data, and then we have historical and prehistoric evidence by using proxies, oxygen isotopes in shells of animals in the ocean, tree ring data, sediment core data, ice core data, all these pieces of information we've gathered to help us understand what the climate used to be thousands or tens of thousands or hundreds of thousands of years before now. And that's what we're using to investigate climate change. Here's the main issue that we're dealing with: climate. The greenhouse effect is being impacted by carbon dioxide. Carbon dioxide is emitted from the burning of fossil fuels and a whole bunch of other things, but primarily the burning of fossil fuels up into the atmosphere. It's clear, it's tasteless, you can't smell it, you can't see it, unless it's in high concentrations. It's a light blue. And we have plants that photosynthesize. They take up CO2. So we have the producers of CO2 and we have the uptakers of CO2. So keep that in mind as we go through. So the first measurement of carbon dioxide in the atmosphere was done by a fellow named Charles Keeling, started in 1958, and measured it continuously on until today. And basically, you see all these up and down lines. The red lines are actually the measurements of carbon dioxide. He did this at the Mauna Loa volcano in Hawaii at 11,000 feet. And the blue line is an average over each year. So we're looking at this and we can see that the carbon dioxide in the atmosphere is increasing, increasing, increasing. The up and down movements, if we look over here, are basically in the springtime in the northern hemisphere, different than the southern hemisphere. In the northern hemisphere, springtime, the leaves start coming out, and when the leaves come out, we have more photosynthesis. More photosynthesis takes up the carbon dioxide from the air, and it's depleting. It's actually depleting the CO2 in the air, reducing that concentration. So the concentration of carbon dioxide goes down, 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 until the fall when the leaves drop off. They're not photosynthesizing, they're not taking up that carbon dioxide and reducing its concentration in the atmosphere. And then it starts going up in the winter again, all over again, every annual cycle. So that's basically how the carbon dioxide cycle works in the atmosphere. And right now, we're up and around, somewhere around 400 parts per million. That number doesn't mean anything particular, it just means that we're reaching higher and higher concentrations all the time. So here's that Charles Keeling slide back to 1960. Let's look farther back, a little bit farther back, maybe 1,000 years ago. Here's the concentrations that the Charles Keeling curve covers, the ones that we actually measured since 1958. If we look back in time, all of these measurements, all of these dots are different data points from ice cores. There are 4 different ice cores here, and we can tell based on these proxies that throughout the last 1,000 years, this is the carbon dioxide concentration in the atmosphere, and all of a sudden, there. Okay, ever since the beginning of the Industrial Revolution, 1750 to 1800 basically, we started increasing very, very rapidly, and this is what's called an exponential curve, or a hockey stick curve, and we are right here now. There's no indication that it's going to go back down, we're just going up continuously. So that's the problem that we're having. This carbon dioxide is a heat-trapping gas in the atmosphere. It's concentrating carbon dioxide and increasing temperature. So let's go back even further. Let's go back to 400,000 years ago. We've been through several ice ages. This is the track of carbon dioxide in the atmosphere through those different ice age cycles. We were actually due to have another ice age cycle here because the concentration went up. However, it didn't go back down. It's continuing to go up exponentially. And right now, in July, a couple months ago, we're now over 400 parts per million in the atmosphere. So what are we going to do about this? Well, there's this group of scientists, like I said, the thousands of scientists that are working on this, called the Intergovernmental Panel on Climate Change, or IPCC, have done a number of reports starting in 1990. About every 5 to 7 years, they put out another series of reports analyzing, reanalyzing, looking at what the data was, what the new data are, and trying to evaluate what this all means. Okay, so this last year, 2013, is that on the screen? Yeah. They put out there's 3 working groups that were doing this. And this is, again, from the whole globe. Working Group 1 did the physical science basis of climate change. Working Group 2 did impacts, adaptations, and vulnerability. Working Group 3 worked on mitigation of climate change. And finally, they put out a synthesis report incorporating all of the information that was in these reports through this last AR5, the Assessment Report 5, 2013-2014. So they're producing the most recent information that scientists are gathering on the globe. So if we look now at global carbon emissions, that means all of the countries of the world, who's producing this stuff, how much is out there. We're looking at carbon emissions in this scale here, and that metric is actually 1 gigaton of carbon. So we've got about 7 or 8 gigatons of carbon. Even though it's a gas, it still weighs something out there in the atmosphere. And 1 gigaton is equal to 10 to the 9th tons, or 1 billion tons of carbon dioxide out there. Okay? So what are we doing here? Back in 2000, we were measuring stuff up until about the year 2000. We started doing models. We started developing models that would project and predict what the possible consequences of carbon dioxide in the atmosphere would be. And I'm going to show you 3 different scenarios, in other words, assumptions of what would happen if we followed those assumptions into the future. So the B1, Integrated Ecological Friendly World, this is the low emission scenario. This is if we don't produce much carbon dioxide in the world. The second model type is A2, the divided world, and that's basically business as usual. If we go on just like we're doing now, we're going to have this result according to the models. The third one I'd like to carry through the talk is the A1FI with an integrated world, but this is called the fossil fuel intensive. we can have an integrated world between the countries, but if we're still primarily focusing on burning fossil fuels, that isn't going to help us much, and that's the high emissions scenario. So the low emissions, middle of the road, kind of business as usual, and then the A1FI. So each one of these has a different color, and each one of these lines is projecting the model results of what it would be, how much emissions, how much carbon dioxide emissions we would have if we use those assumptions. And then what we have is these black lines, the solid line and the open line, all of these lines here following up. Those are the actual measurements that we've made in addition to the model runs. And what we're seeing here is that basically the measured emissions that we have in the black have all exceeded the estimated or projected emissions that we have. Except maybe down here we had this little inflection point here. What happened there? We were going along higher and higher and higher than we ever projected before. And in terms of these reports that come out, every single set of reports that come out, it's actually worse than the last one that we projected. So we're trying to improve our models that help us understand what's going on. So let's take a look at this inflection point more closely. Here's that inflection point up here. What happened then was this was the global financial crisis around the year 2008. If we go back, there's another inflection point down here. That was the Asian financial crisis in early 2000. The collapse of the former Soviet Union was another inflection point. At each one of these times, the carbon emissions from all the countries of the globe went down. Went down because they were having financial crises, because they weren't burning as much fossil fuels, the economies are going down. And that's the reason. There's another inflection point in 1980 or so, the US savings and loan crisis. And finally, the oil crisis in the mid-1970s. So each one of these affects the global production of carbon dioxide, which affects the temperature. So who's producing these global emissions? Let's take a look at that. If we look at 1850 to 2011, the United States, in this blue, was the highest producer of carbon dioxide. And number 2 was the European Union. Number 3 was China. If we then change that time frame from 1990 to 2011, the US is still up there, but China has moved up to second place. There's a lot of other things here that interest you as well, but as of November 2014, about 9 months ago, China has surpassed the United States. They actually did that about 8 years ago. China passed us out in terms of global carbon emissions. And India is coming up rapidly as well. So the developing countries, China, India, are really producing so much more carbon dioxide emissions than they were before. So it's important that we understand what's happening. Now, yes, China has a lot of different has a different economy than we do. However, they are moving forward rapidly. Right now, China is number 1 in wind energy development, away from fossil fuels, and they're number 2 in solar energy development, again, away from fossil fuels. They are going to surpass us in altering their use of energy to non-renewable, renewable fuels instead of non-renewable fuels. So Germany is actually number 1 in solar. So they're going to pass us out in terms of developing solar and wind in the very near future. So we don't discount China in terms of how we're going to solve this problem. So let's talk about temperature. We already talked about the greenhouse effect, and let's look at the heat. Global hottest year, 2014 was the hottest year on record over the past 1,200 years. Okay. We're not working, Biz. Oh, there we go. A little delay there. I guess it's too hot in here. 2015, so far, will likely beat that record as the hottest year on record, with July of 2015 as the hottest month ever. And 13 out of the 15 hottest years on record have all occurred since the year 2000. The odds of that happening are about 1 in 27 million. And that marks 38 straight years of above average global annual temperatures. Now I'm going to move along and give you kind of a smorgasbord of information here. A lot of different topics. It's extremely complex, many different dimensions. This is going to give you some economic and policy implications, but I'm going to try to focus on the science part. So as CO2 concentrations are increasing, so are the temperature values. So we're getting hotter and hotter and hotter all the time. So I'm going to give you, let's see, I'm I'm going to give you a sense of how the temperature has changed on the Earth. If I can do this. Oh, no, no, no. I need to go over here for a second to initiate this. There we go. There it is. Okay. So here's a time lapse of temperature on the Earth. The blue cool end means that the temperatures have gotten cooler. The red end means that the temperatures have gotten hotter. And the white in the middle is no change. Okay, so over time, 1930s, 1940s, 1950s. Notice that all the different areas of the Earth are responding in different ways in different temperatures. Some are getting cooler, some are getting hotter over time. Go into the 70s, into the 80s, into the 90s, and into the 2000s, stopping at 2006. What does that tell us? Tell us that the Arctic has been warmed the greatest, which also means that we're having a lot of ice melting in the Arctic. It's affecting a lot of things, and actually even affects some of the huge snow, the cold air that's come down from the Arctic, affecting some of the New England massive snowstorms that they've been having as well. So how do we measure, how do we project and predict what's happening with the temperature that's going into the future? Most of the models are worried about what's going to happen by the end of this century. 2100 is a typical model run of where we want to go and see what's going to happen. So here we are in the year 2000 when we started these models again. You're here, 2015, and let's take a look. If we just stop at 2000, this would be where the temperature increase would be. So looking at the beginning of the Industrial Revolution, 1800, 1750, we want to know how much temperature can the Earth stand, how much increase. And there has been a lot of treaties and a lot of information, and scientists and governments back in the 1990s, they determined that 2 degrees centigrade was about as far as we want to go to protect us from massive climate changes and impacts on the Earth. So we're trying to keep below the 2 degrees centigrade limit. So if we stop at 2000 level, we'd be fine. If we went to the low emission scenario, remember I showed you that earlier, would be somewhere up here in this projected area. If we went to middle of the road scenario, a little higher. Business as usual, a little higher. What they didn't show on here is this last one over here, which is the fossil fuel intensive, and that brings us up to this bar here indicates the potential temperature, up to maybe even 6 degrees centigrade above the old industrial complex, not the industrial complex, the 1970s, 1800s or 1750s, start of the Industrial Revolution. So here's the low emission scenario again. Here's the fossil fuel intensive. So the low value and the high value in these models. I'm going to stick with me here. This is a little complex, but I'm going to walk you through it. So here's an average temperature from 1950 to 1999. This is degrees centigrade. This is degrees Fahrenheit. They're not the same. So initially, this low emission scenario goes from the bottom of this yellow up to here. That's the range of possible outcomes. If we look at the next one, the high emission scenario that starts here and goes up to there, this is the high emissions range of possibilities. And in the middle is this orange, which is the overlap between these two sets of estimates on into the future. Now, if we just use the mean values, this is the average values for those two sets of models. This is the range of expected temperature increase. If we look at, that's in Fahrenheit. If we look over here in centigrade, that's about 3.5 degrees to 6 degrees increase in temperature on the Earth. So in order to protect us from getting up to 2 degrees centigrade, we need to stop somewhere over here. If we go over to that high emission scenario and pull down, that'll bring us to about 2030, 2035. If we extend that onto the low emission scenario and project that down, that's somewhere around 2040, 2045. And that temperature is actually 2 degrees centigrade, but it's about 3.6 degrees Fahrenheit. So 2 degrees centigrade, we're still trying to keep below that. we might have time into 2030 or 2040 to solve this problem. That doesn't mean we start solving the problem in 2030. That means we've gotten there by 2030 in order to keep this at or below 2 degrees centigrade increase. Okay? I'm sure you all got that. All right. So where are we now? We're at 2015 right now, and so far we've actually increased the global temperature by almost 1 degree already, which is not very good because we're probably not going to be able to keep below 2 degrees centigrade increase. We don't even have an agreement to keep it below there with the countries in the world yet, and we'll talk about that later. So let's bring it a little closer to home. Instead of globally, let's talk about Northern California. This is work from the U.S. Geological Survey. Here's the emission scenarios that I told you about before. Each one of these colored lines is another model run projecting what would happen in the future. So here we are in 2015. So let's see what happens. Looks like there's above the 0 line means changes into the future. Looks like temperature is going higher and higher. 20 out of these 23 model runs project roughly a 2 to 3 degree increase to up to 6 degrees increase. So somewhere in there, this is what the projections tell us using these different models. 23 different models are producing similar kinds of results. Now let's look at precipitation. So this was temperature. Let's look at precipitation in Northern California. Here we are in 2015 again. Looks like there's a large uncertainty with respect to precipitation. Here's the 0 line. This is where we've been down here. This is where we're going to the year 2100. And most of them, 19 out of the 23 model runs projecting into the future, tell us that it's a little bit above and a little bit below the 0 line, which means we really can't predict very well or project very well what the temperature, what the precipitation, the rainfall is going to be like in the future. So let's talk about precip. Is it going to be more rain? Is it going to be less rain? Is it going to be floods? Is it going to be droughts? We can expect either or both. We are having both now. If you read the news, if you look at the TV, you're noticing we're having droughts in some places, we're having massive floods in another. It's exactly what's happening. I'm going to pass over that one. Atmospheric rivers, or what the meteorologists like to call the Pineapple Express. These are rivers of water in the sky, about a mile high and about 250 miles wide. This is San Francisco Bay. Here's the west coast of California. I guess we only have one coast in California. However, when the big one hits, we will have an east coast and a west coast. Okay, so this is massive amounts of rain and it's precipitation hitting the coast. Now I'm going to show you, okay, I already told you that. I'm going to show you another simulation. And so this is a huge superstorm that occurred in December of 2010. Here's the ticker right here. You can see how there's a 5-day storm. You can see the dates on here. There's the 22nd. It replays itself. Here's the 17th, 18th, 19th. So here's Hawaii. This is the open, the tropical Pacific. And this is layers of moisture moving into the coast, the west coast of California. And you can see, if you look carefully, most of that moisture is hitting in southern California. Unfortunately, most of our reservoirs are in northern California, so that doesn't help us much. Even if we had massive rainfall, we're not going to be able to capture it as much to enable us to help us use that water later on. So atmospheric rivers are typically hitting us in Southern California over time, and that is a problem. I mean, it's good for them, but not so good for us up here. So I won't go there. Okay, so there's massive flooding, massive amounts of precipitation. On the other end of the stick, just as we showed in the graph, we could have a lot of rain, we could have very little rain. In fact, we are in the 4th year of a drought in the West. The rest of the country is not being affected like that. The West is. And here's a closer look at California's drought situation right now. And I've been told that they had to create a new color to create this exceptional drought that we have in California. With that drought, where's the water? The water is not here. So they have to pump it out of the ground. The farmers in San Joaquin Valley are pumping out of the ground. And the problem is it's not like a big cave down there. These are all sedimentary features, sedimentary layers. And once you pump the water out, it collapses. There's no way to reinvigorate those those strata with water. Once it's down, it's going to stay down. So there's no more holding area. And the people in California, in San Joaquin Valley, they are pumping, and right now the valley floor is sinking 2 inches per month. And just to show you, I mean, this is not just this year, not just the 4-year drought. This has been happening for decades. So here's a good example. In 1925, here's the land right there. You see a little man there. That's not a little soldier guy, plastic soldier guy. That's a real person. In 1925, the land used to be up here. 1955, they pumped it so much that the land is collapsing. And then 1977, it was down here. Land has subsided like 28 feet in some areas in the San Joaquin Valley. I think most people know that, but here's just a visual to show you. And today it's subsiding about a foot a year and continuing. The more we pump, the lower it goes. Okay, so what happens with snowpack? If we have the low emission scenario here, we are expecting about a 60% loss. If we do a higher emission scenario, we're expecting an 80% loss on snowpack in the Sierra Nevada. This is Governor Brown and a representative of the California Department of Water Resources. You've probably seen this on the news. Every April 1st, they go out and measure the water equivalent in the snow. Same place, exact same place, same time every year. That was April 1st, 2015. No snow. That diagram right there was that he's pointing to, that mark on the core, was the last lowest snow recorded. Now there's nothing. So we're affected by this drought. We're affected by less precipitation, and as they take these measurements all over the Sierra Nevada, we're down to 5% of normal. And here's the snow drought measurements, 1982 to 2015, were the lowest we've ever been. And because of that, we've got lower humidity, lower precipitation. Everything is drying out. It's tinderbox out there. Great sunsets. We had a great sunrise this morning from the Butte fire. And in the west, temperatures have been increasing almost a degree per decade. Here's a graph that shows in the orange line and the orange circles temperature increase, and the red bars represent fire abundance or frequency as we go from 1970 to 2012. Fires are increasing, you know that. You've seen it every day. This is a really neat little interactive website, interactive wildfire tracker. Here's North America, the United States, and this was about a week ago, the climate tracker through Climate Central. You go to the Climate Central website, you can do this. So this is the big Chelan set of fires up in Washington State, some fires in California, and Alaska, which has been just slammed with fires this summer, as you all know. So you go there, you can actually home in, you get a bigger area of map, and you can get specific information on specific fires, how long they've been going, what their percentage of coverage is, and great website. Okay, going from drought to wet, we've got sea level rise. All of the coastal areas in the United States and the ones that will happen after California breaks off are all going to be subject to sea level rise. Here's an Alaskan glacier calving off because the warm waters are affecting it more. And island nations are going to be having a really tough time. So let's look at that. The sea level itself is really controlled by so many different factors. I'm not going to bore you with all of that. But what I do want to tell you is that sea level rise is primarily due to about 50% from the melting glaciers and ice caps, and about 50% from the actual seawater expansion. The sea is heating up. The ocean takes most of the heat that's hitting the earth. And when you heat water, it actually expands. So 50% of that sea level rise is actually from the water expanding. So this is a report from the National Research Council in 2012 discussing what would happen in California, Oregon, and Washington specifically. So we're looking at projections for the year 2030, 2050, and 2100. And this is how much sea level rise we're expecting over that time. So for the year 2030, we're expecting that we might get up to about 30 centimeters, 35 centimeters rise in sea level by the year 2030. If we look at the year 2050, we're going to be expecting up to about 60 centimeters of sea level rise. And for the year 2100, we're going to be expecting up to about 1.6 meters of sea level rise, which is actually about 5 feet. So you can expect to not have to travel so far to get to the beach. What's interesting is that over the last 30 years, this is a plot of increasing sea level in the West, specifically, done by USGS people. The sea level has maintained its level here in the West. Now, we don't know exactly why. That's not around the globe. That's just in this local region. But because there's wind patterns that are changing now, we believe that wind patterns and currents are changing. We're probably going to see that sea level rise increasing again like it is around the globe. But in the West, we've seen a hiatus of sea level rise more recently in the past few decades. Atolls. How many people know what an atoll is? Good. So for the rest of you, atolls are coral islands, round coral islands that were formed from either a volcano or a mountain subsiding into the ocean, and coral growing on the edge of that amount, growing to the surface. And they pretty much almost always are in some kind of a circular pattern. However, because of the way they were formed, most all atolls are in the Pacific, tropical Pacific. They're only about 6 feet above sea level. And that's a problem for people like the Maldives people who have populated a little bit some of their islands. And with a 6-foot rise in sea level, which is what we just saw as a prediction, they might have a hard time getting to the grocery store. So there are actually a number of island nations around that are already experiencing sea level rise problems in their area. And I'll just tell you about a couple of them. The Carteret Islands, which are a part of Papua New Guinea, right here, are having to move because of sea level rise. Papua New Guinea has been taking them back to the back to the mainland of Papua New Guinea. The Tuvalu population has about 10,000 residents, and New Zealand has agreed to take those population. The Kiribati Islands, quite a number of them, they have 110,000 people on those islands, which I showed you. And they just recently bought an island from the Fijians for $9 or $10 million, and they're going to move their 110,000 people, not onto that one island, but probably onto several islands in that area. So these are island nations that are being displaced already. There's also coastal areas. The Shishmaref Inupiaq Eskimos are on the west coast of Alaska, and they've been pretty much protected by pack ice. Now the pack ice is disappearing in Alaska, and those waves are moving up and they're affecting and destroying their villages. So they're going to have to move as well. Okay, let's come a little closer to home. The ocean is not a flat surface. If we look at Seattle and Washington up in here, compare it with San Diego, the Seattle area is about 8 foot higher in sea level than San Diego is. So huge differences. If we look a little closer to home, this is San Francisco Bay. And what's interesting is that the South Bay in San Francisco is about 4 foot higher than Suisun Bay. Very close, but they're actually higher because of the currents and the way that the water moves in and out of the bay. So what's happening in those areas? What's happening in the South Bay where we have this much higher level of water? So let's take a look at what would happen in a 100-year storm surge. Here's Palo Alto. This is 101. Okay, keep an eye on this bay right here. Okay, this is the South Bay water. This is people and infrastructure here. I'm going to show you no sea level rise at all, just a 100-year storm surge coming through. Boom. That bright blue is just a 100-year storm surge, would cover that area. If we added 50 centimeters of sea level rise, we would be up in this light blue area. If we added 100 centimeters, would be in the yellow. And if we added 150 centimeters of sea level rise, would be out to the red. 150 is very close to 160. That's what we projected for California by the year 2100. So let's take a look. What is in this area that would be affected? So there's a few Silicon Valley places there. Let's see, Intuit, Google, Yahoo, What else do we have there? Intel, just a few small companies, so we don't need to worry about that. But I do want to ask, how many people own an iPad, an iPhone, an iPod, Apple computer? Okay, so you guys are okay, because right here is Apple's corporate headquarters in Cupertino, so you're good. Okay? The fact that my son works for Apple doesn't mean anything. You just keep buying your Apple products, okay? So these places are going to be affected, no question about it. But Apple is going to be fine, so keep your stock up. Okay? Oh, sorry, I don't know where that came from. So upwelling in El Nino. San Francisco, fog. We want to talk about coastal upwelling because it's really important in terms of what happens on our coast. So let's assume we're in the north, looking down our coast towards San Francisco. This is north, this is south. The winds, the typical winds blow from the north down the coast, and they actually spiral around because of the way the Earth spins on its axis and what we call the Coriolis effect. The water is pushed off the surface, away from the land, out to sea. That leaves a deficit of water here, and that water is replaced from the bottom, from 1,000 to 2,000 or many thousands of feet down. The water is cold, it's nutrient rich, and when that warm air, when the cold water hits the surface, we get fog. That's why you see what you see in San Francisco. In fact, there was a person, let's see, I think there was a person that said the worst winter I ever spent was a summer in San Francisco. Who was that? Very good. Okay, you get an A for this lecture. Okay. In addition to getting the fog, we also get nutrients, nutrient-rich water. That nutrient-rich water helps support food for these tiny microscopic plants called phytoplankton, which in turn produce food for microscopic animals, the zooplankton, which then feed the small fish, which feed the larger fish, which feed the birds, the marine birds and mammals, and it ends up being a very productive marine community. That's when the winds are blowing down from the north. However, when we have an El Nino event, those winds are depressed. The winds stop blowing. The water stops moving up from the deep ocean. The nutrients stop, and you get a crash. That entire system crashes. You don't get any phytoplankton, no zooplankton, no small fish, no big fish, no birds and marine mammals populations. They do not reproduce in those years because there's no food. So people are looking carefully at El Nino events. There are some scientists are finding increased El Nino events as a result of this climate change process. Where do we find these upwelling zones that we have on our coast? Mostly on the west coast of continental land masses. We find these. And El Nino events, again, slow the winds, slow upwelling, and cause major disruption to marine communities. Okay, we are in an El Nino process right now, this year. This was updated just 2 days ago. I updated this chart from the National Oceanic and Atmospheric Administration. You're here, they do this 3-month running average, so August, September, October, November, October, November, December. Here's the 2015-2016 split. And their projections are, this is the percent of likelihood of having an El Nino. Well, we're in the middle of an El Nino right now. And they're projecting with 90% plus certainty that we're going to continue having an El Nino process or event on through January and on into the spring of 2016. You can go to their website. Here's the information down here. Just write that down quickly as I go. But as we come into the fall season now, we may expect a lot of that precipitation in typical El Nino events in Southern California. So if you can't see that, this is North America. Here's Alaska. Here's the Baja down here. And so you can see that in Southern California and the southern area of North America, we will experience typical wet conditions during an El Nino. However, in Oregon and Washington, and in Alaska, they may experience warm conditions. So an El Nino is not an El Nino the same everywhere. It's very different in different places. What it does also typically predict, though, is that during an El Nino, you will have increased Pacific hurricanes. And you may have seen on the news, we're getting hurricanes in this area now. And what we tend to do is have decreased Atlantic hurricanes during an El Nino. So it's very different in different places. What are the biological and ecological effects? And again, I told you, we're doing a little smorgasbord here of everything. We're experiencing phenological changes. We have the changes in the timing of ecological processes, like when are organisms abundant? Where do they migrate? When do they migrate? What are the migration patterns? What's the distribution? What are the breeding seasons and related processes? What's their reproductive output? And, when do the birds and the bees and the trees all reproduce? This is all changing because, in fact, we're seeing spring occur earlier every year. In some places, up to 5 days earlier. The red states, not those red states, the red states are the ones where we have 5-day increase in spring. And what happens, we have temporal mismatches, migration patterns, and migratory predators and prey. The birds eat the insects eat the plants. If those plants have not grown yet in the spring, they're out of luck. If the insects haven't been there when the birds migrate there, they're out of luck. So we're having problems with mismatches. And blooming flowers and pollinators. If the pollinators aren't there to pollinate the flowers, we don't get another set of flowers the next year, or the plants might die. Mismatches. Increased water stress or possible vulnerability to frost damage if it happens too early. And it happens in the marine environment too. Maine lobsters molted 15 to 30 days earlier than they normally do in 2012. Everything is heating up, everything is changing. Mussel beds along the coast of California. Actually, these occur from Alaska all the way down to the Baja. This is the mussel Mytilus californianus. This is what I did my PhD on. If you look closely at a mussel bed, you'll see these mussels here. Sometimes they're 6, 7, 8 mussel layers deep. And they have all these other animals growing on them, animals and plants. And it turns out that there's over 300 species of other individual organisms, everything in there. This is what I did my PhD on, 300 species. And what's happening is that all those associated organisms in those mussel beds are declining. From 1960s to 2002, they declined maybe 50%. So things are changing everywhere. And we get the sea star wasting disease in 2013. We get lesions. These things are just melting. This used to be a sea star down here. Losing their arms, their legs. This one is almost completely melted. And what's happening is it's caused by increased temperature and more pathogens, viruses and bacteria are affecting them. What's OA?
Ocean acidification.
Very good, thank you. Ocean acidification. So we saw this curve here. This is the Charles Keeling curve. Atmospheric carbon dioxide is increasing over time up to about 400 parts per million now. At the same time, the ocean surface carbon dioxide, because the atmosphere is touching the ocean surface carbon dioxide is also going up. As that happens, the ocean pH is going down. As you go down in pH, you increase the acidity. So what you have is increased acidity in the ocean. This decreases and lowers the saturation of calcium carbonate in the seawater. Calcium carbonate is what marine animals use to build their shells. If they can't access the calcium carbonate, they can't build a shell. If they can't build a shell, they're gone. So now we're going to have a chemistry lesson here. No, I'm not going to do that. I'm not going to bore you with the chemistry. It's fairly complex. But basically, I wanted to show you that since 1850, the world's oceans have experienced a 30% increase in acidity. And we're continuing on with that. That's affecting all of these guys here. Everybody that uses calcium carbonate to build an internal shell or an external shell is affected. So here, by the end of this century, it's predicted the ocean surface will be more acidic than it has been in 400 million years. I'm going to pass on that. So where do we go from here? Actually, I'm not going to pass on that. This is a study that I'm involved in right now, looking at mussel shells. And the mussel shells are made of calcium carbonate, and they have a certain thickness. We've collected shells from the years 2000s, from the 60s and 70s, and from Indian midden shells. Middens are garbage dumps where Indians had dumped their food, and they used to eat mussels from 1,000 to 2,000 years ago, comparing the thickness of the shells 1,000 years ago, 1960s, and the 2000s. And what we find is, here's the midden shells, quite thick, the 1960s and 70s, and the 2000s. You can see that decline. This is the thickness of the shell. Total thickness, thickness per shell length, and thickness per shell age. seems to be decreasing over time. So is that due to ocean acidification? We're not sure because we don't have enough data from those times back then, but it's possible. So where do we go from here? Paris, let's go to Paris. Okay, why not? It might be better than the fires we have here. It turns out that the Conference of the Parties, number 21, is going to happen in November 30th to December 11th. This is the World Climate Summit. This year is happening in Paris. And this is the result of all these studies that were going on, and policymakers and legislators. They are all convening to work on the United Nations Framework Convention on Climate Change. They've been working on this for decades and decades. Last year, it was in Lima, Peru. That was the Conference of the Parties, number 20. 194 countries participated. We have about 194, 95, 96 countries, depending on who claims that they're a country. But the goal is to develop an agreement whereby the international community would work together to keep global warming at or below 2 degrees centigrade increase or 3.6 degree Fahrenheit increase from pre-industrial levels. That's the goal. That's where the 2C or not 2C comes from. And is hopes to achieve a legally binding and universal climate agreement between all countries to be completed this year, but implemented by the year 2020. Now, will we get there? I don't know. Many countries will not sign an agreement unless the U.S. and developing China and India agree to a legally binding resolution. Well, that's fair. However, for the U.S. to sign on to a climate treaty, it must be passed and ratified by both houses of Congress. Easy, no problem. As you can guess, there will be some disagreements. However, there is still time. We can do this. We need to do it sooner than later. Okay? And the bottom line for my talk is that I know there are people who disagree with the fact that there is global warming. I respect their opinion, but I've found definitive proof that there is global warming, and I just wanted to show you that proof. There it is.